My name is Filip Leonarski. I am Beamline Data Scientist at the Paul Scherrer Institute, and I would like to give you a second part of my talk about implementing X-ray detector data acquisition system using OpenCAPI. So, in the previous talk, I have presented to you the challenge, and in this talk, I want to give you a solution. Now, a quick recap. So experiments at large research facilities like Swiss Light Source produce enormous amounts of data. As I have shown you in the previous module, exponential increase in data production is happening. And it's not only for Swiss Light Source, but this is also for facilities like CERN or other places. For us, the current challenge is to handle 50 to 100 gigabytes per second in the coming years. Processing and analysis of this data on the fly is actually very important for success of experiments at Swiss Light Source. As experiment time is scarce, our users are usually given shifts of 8 hours. If they know the outcome of their experiment while they are doing the measurement, it helps them to plan decisions, to make decisions during the experiment. And they can better use that time allocated at the Swiss Light Source. Economics is also important. So operating the facility becomes more and more expensive because of the data rate challenge and because of the rising costs of IT infrastructure. And to help with handling the data, FPGAs seem as the most promising solution, but they are expensive in development, even though they would be perfect in operation. Why FPGAs are perfect? Because they have real-time performance, so they are cycle accurate. We know when the design is developed for an FPGA, what is its latency and throughput. FPGAs can offer great memory throughput. So with high bandwidth memory, it's possible to have 460 gigabytes per second bandwidth to memory as large as 8 gigabytes. They also have network on board. So many FPGAs have network hard cores for speeds as fast as 100 gigabit per second, or currently there are even introduced chips with 400 gigabit per second bandwidth of the Ethernet. But the problem with FPGA development, it's difficult and time consuming because it requires to develop software and hardware description languages, and it requires a very good knowledge of Linux kernel to be able to design device drivers for PCI Express. Now, the first problem of using this very specific hardware design languages that are known to electrical engineers and often not to us programmers is a tool called high-level synthesis that was already introduced in part 6 of this course. Just as a reminder, high-level synthesis is a compiler that transforms C or C++ code into a hardware design language. So all code that is used by high-level synthesis is a valid C++ code that can be executed on a CPU and the execution on CPU is functionally equivalent to run on an FPGA. So the end result should be the same. Of course, performance is different, and running on a CPU, we don't get the proper parallel behavior of the code. So there could be deadlocks that cannot be debugged with high-level synthesis. There are dedicated pragmas to guide FPGA synthesis, and the code is in general understandable for software developers, but code may look strange. Now, coming to how to connect the FPGA with the CPU, a current industry standard is PCI Express. PCI Express is made for peripherals like network card or sound card. It operates via direct memory access. So it is accessing memory using physical addresses. And it's a job of a kernel driver to actually translate virtual addresses that are known to a software developer to physical addresses that are given to the device. Now, it's a simple operation to go between virtual addresses and physical addresses. But any error in this operation can have catastrophic consequences for your operating system because you may be writing to a wrong location in your memory. It's very dangerous. Everything that happens with the kernel has a high risk of making issues to the operating system. So there needs to be a lot of work to ensure that kernel drivers are correct. And to develop kernel drivers, you need to have a lot of understanding of CPU and kernel memory mechanisms, like streaming memory or consistent memory, like pinning, like cache coherency. And actually, OpenCAPI is something that helps you with all of this. For me, actually, OpenCAPI is this cable that connects FPGA to a host CPU, in this case, Power9 CPU. It brings it brings access to virtual memory, and this is like what happened with 80 to 86 CPUs that brought virtual mode to software development on a CPU. So FPGA connected via OpenCAPI to a host CPU sees virtual memory. All the translation between virtual memory and physical memory is done by the CPU, the same like it's done for software. It's using transaction look-ahead buffers, and it offers security, reliability, efficiency, and coherency that is available currently to software. This is also available for the accelerator. With OpenCAPI, you need only a single kernel operation, and then the accelerator is attached to a running process, and everything happens via virtual memory. And it's quite important because for me, as I'm trained as a software developer, it brings a familiar environment because I always learned to program in virtual memory space, not dealing with all the possible issues coming from physical memory. It provides simplicity because the middle layer between OpenCAPI FPGA and the application is much smaller as in case of PCI Express because there is no driver. And also, this middle layer is very generic, so I don't have to adapt this middle layer to my particular application. It will suit all the possible applications. And it also helps with verification because high-level synthesis code designed for OpenCAPI can be easily tested for correctness on a CPU, excluding parallelism and performance. So it makes the development easier and cheaper at the end of the day. Now, there is a thing called OC Axle that is a shell maintained by IBM. It's fully open source. You can go to GitHub and you will find this OC Axle there. It provides tools that help you start working with OpenCAPI. It helps you to set up transceivers. It helps you everything up to an AXI memory mapped bridge where you can connect your application to OpenCAPI. It also helps you to provide pre-configured interfaces like high bandwidth memory, Ethernet, or NVMe. And it provides a simulation environment where you can simulate both your software part that is running on a CPU and your hardware design running on the FPGA in a single simulation that is very close to an actual hardware execution. And right now, I want to switch gears and give you some ideas about the actual implementation of data acquisition pipeline called Jungfraujoch that we are currently working at the PSI. So Jungfraujoch, we want to deliver a single 2U IBM Power 9 server that will be able to handle 50 gigabytes per second bandwidth. This will be possible with up to 4 FPGAs running in the system. And what we want to do is we want to do data acquisition, we want to do initial data analysis, and a pre-compression. It's designed in a modular way. So there are multiple modules. You see them labeled here in blue. And each of these modules is a separate C++ function that is connected with the other modules via AXIStream FIFOs. So between all of these blue squares, there are just FIFOs communicating the data going through from left to right. In this design, it's easy to add additional cores because you just add a function and just need to modify the FIFOs. What is important is that each of these blue modules will only work on streaming data. So we assume they don't have a memory to actually know the whole image as it's going through. This is how it actually looks when implemented on the device. You can see different cores present in different area assigned by the Xilinx tool. You may see, for example, that gain here in pink is close to HBM because it actually heavily uses HBM. So there is a clear logic in this placement. What is really cool about FPGAs is the power consumption. I was quite amazed when I had a look on my design and I saw that it only takes 18 watts per board for the whole streaming functionality. And this compared with running the same functionality on a server, which would take probably hundreds of watts or even above a kilowatt. So there is a clear saving in energy by using FPGAs and OC Axle. A quite important part is about the testing. So actually, I'm doing two kinds of tests in my pipeline. I have software tests. Executing a software test takes seconds. I take the high-level synthesis code. I integrate this with my software code. And I compile everything with GCC. And I use Catch2 framework to test the outcomes. In this way, I can cover multiple functionalities and scenarios. I actually have above 90% of HLS code coverage. And this allows me to ensure that functionality of my code is okay, that I don't have errors in calculating memory addresses, that arithmetics is done properly with fixed point integers. I can test all of this. Still, the design can fail on the device because of deadlocks in FIFOs. And to help with this, I'm actually doing hardware simulations. Now, a single hardware simulation for a single scenario takes for me hours, between 2 to 4 hours. So I have a much smaller coverage of the code. I'm only covering 1 or 2 scenarios, but this is enough to tell me that there are no deadlocks and that um, the tests from the software are actually consistent with what I get in hardware. So as software tests are cheap, I'm actually doing them either from the IDE or I script them in GitLab to be running as a part of a continuous integration pipeline. Now, if software tests are failing, I know that my code is wrong. If there is success for the software test, then I'm actually running hardware tests. So also hardware tests are part of my continuous integration pipeline. And so I can know if I change the high-level synthesis code, if this also results in a proper behavior both in software and hardware tests. And then finally, as a part of my continuous integration pipeline, I'm also building images to see if there are any problems with time enclosure in synthesizing the designs. And this is actually working. So we have been able to use the OpenCAPI system already for some time. We were given a crystal that was already measured at our beamlines of a SARS-CoV-2 nucleocapsid phosphoroprotein, but this crystal was measured in 1 minute with conventional detector. Now we have taken our Jungfrau detector, we have taken the Jungfrau-Joch OpenCAPI-based readout system, and we collected 2,000 images in a single second, and this was enough to solve structure of this protein. So this system is really working. It can be really used to solve atomic structure of proteins at a very high speeds. And the gains are real for us. So currently, being able to show operation of this detector with a 4 megapixel system, we are already 4 times faster than running on a mainstream hardware. We also have a decrease in price of 4 times versus conventional hardware. And we have even higher decrease in power consumption of the system. Now, shortly, we hope to be able to demonstrate with the same computer, just stressing it a bit more, to run a 10 megapixel system. This would show at 10 times, an order of magnitude higher acquisition and conversion bandwidth as compared to mainstream hardware. And then 10 times decrease in price for the performance. We would even show a 20 times decrease in power consumption. And with this, I would like to thank multiple people that were involved in the research I presented in these 2 modules. And I would like also thank you for listening to this presentation. Thank you.